Thank you, Amina Sama. My name is Andrei Kolarik, for those who don't know me. And today I prepared for you a presentation about our analytical tool Adbian, which we are preparing or developing in Europe, and which we would very much like to show you and to hear your feedback if this is something that could be useful on Japanese market. I usually like to start my presentation with why is it important, why at least why we think that what we are doing is important. And the main reason for us why we are in this business is that every day big and valuable trees are being cut down just because we don't have precise enough stability data about them. So we tend to stay on a safe side of the decision, and we are cutting down trees or over pruning trees that might be still very stable. The second reason is that consultants often lack tools to support their opinion with objective data. Subjectivity is a big topic in arboriculture in Europe. We have a joke here that if you call 3 arborists to the same tree, you get 4 different opinions. So this is something we are trying to fight with, to provide objective data to a specific tree on which arborists can base their opinion on. And the third reason is that there is just in general not very much tools that can help you to quantify risks with higher levels of accuracy. We have a sonic tomography, we have pulling tests, but these both has its limitations. Not saying that we are trying to replace them, but we are trying to integrate them in our model so we get as precise stability analysis as possible. So the basic concept of Adbian is that we remodel the tree in a 3D space and we simulate the wind loading and how does it influencing the tree. The name itself, Adbian, is short for Advanced Biomechanical Analysis. So it shows you that it's based on biomechanical calculations. You can think of Adbian as a tool to collect advanced tree data. You can also think of it as a device test without expensive hardware, because all you need is your phone, rangefinder to measure the distance, which is few dollars, and altimeter to measure height of the tree more precisely. You can think of it also as a tool for enhancing know-how with technology. We are not trying to replace consultants. We are just trying to give them enough data for them to decide on. And of course, the goal is to dramatically reduce the tree cutting by up to 1/3%. At least that is what was reported by our customers. So what is the added value for you as a consultant? It helps you to decide what to do with the tree based on objective data. It helps you to communicate tree risk with clarity of 3D space, and it helps you to preserve large trees. For tree owner, the added value is that more analysis means less tree cutting and less pruning, which is definitely a trend we see within our users. It means increased safety, and of course, these are the main reasons. So, what is the science behind Adbian? As I said before, it's based on tree biomechanics, which is probably closer to physics than typical arboriculture. And so the tree biomechanics is a stability based on physical properties. We are looking at the tree as an object. And the biomechanics is also focusing on risk mitigation and prevention of unnecessary tree removals. The calculation of biomechanics is based on triangle of stability, which tells us that there is some load, in our case, wind load, that is influencing a structure, a tree, and the tree can react either with material for which we are implementing precise wood material properties, or the geometry, how the material is composed. And that is where we can bring the most improvement compared to other tools, because Adbian, as the only tool on the market currently, is working with real geometry of the cross section and of the tree for the calculation. So there are several stresses going on in the stem of the tree. There is compression by the tree's own weight. There is compression and tension on each side during the wind load. And then there is a growth stress, but it's insignificant and very hard to measure. So we are mostly calculating with these two. But even these two gonna give you pretty complex model of what's happening in the tree. And we're not going to go in such a detail as in how is it precisely calculated, but I just wanted to highlight one value, the W, which is section modulus. Section modulus describes the geometry of a cross-section and its effects on overall stability. As you can see, it's a value that can pretty dramatically influence the calculation. And in a first case study of today, I would like to show you its importance. So with this lime tree, we calculated the wind loading of the sail of the tree crown. And we compared several approaches of how we can calculate the cross-section and the tension in the cross-section. So first, we simplify the cross-section on a circle with the same area as the reality, but simplified its geometry. And underneath, you can see a picture of the real cross-section because the tree had to be cut down. For this, we calculated the section modulus and then safety factor. In the second case, we calculated also safety factor and section modulus for a cross-section of how tomography would calculate the geometry. So we placed 12 points around the cross-section and calculated it. In a third case, we calculated the real geometry of the cross-section. And in the last case, we calculated real geometry of the cross-section with pretty significant cavity in the yellow here inside a tree. And again, calculated section modulus and safety factor. When we compare the results, you can see the real geometry, which is this case, was around 2.6 safety factor. The circle overestimated it, the safety, by 38%. The tomography underestimated it by 23%. So only a difference between this and this was 23%. And the large cavity subtracted from this overall stability 31%, which means that even small differences on the edges of the trees between this and this can have similar effect on the overall stability of the tree as pretty large cavity inside. So this just highlights how important is the outside wood of a cross-section and how important is precisely describing it for calculating tree stability in biomechanics. So this is what we are basing our calculation on. So we started as a simple cross-section, simple cross-section shapes. And with iPhone 3D scanning, we moved to more complex shapes. And in the last step, we can combine it with insights of the cross-section thanks to sonic tomography. Now I'm going to show you how we do that. So first, we take several pictures of the tree with your mobile phone. These photographies can be analyzed, and we can get a rough geometry of the tree from those photographies. Actually, it's 5 photos for every tree. So it's 2 photos of the whole tree and 3 photos of the stem. For the photos, it's always important so the whole crown is visible, the photos of the whole tree. And for the stem photos, it's important so we can see both the land below the tree and the first branches of the crown. This is an example of one tree in the US. These are the photos of the whole tree. These are the 3 photos of the trunk. And as you can see, you are always measuring the distance between you and the tree, so we can model it better in 3D. Why we can model tree even from the photographies better than the other tools is thanks to what we call phone calibration. There is a problem with photographies that they are distorting the reality of the sizes of the objects. If you want to try it for yourself, you can just open your camera and move. You can put 0.5 or the fisheye effect if you have it in your phone, and you can just move with your camera around the room. What you can see that the objects are getting bigger or smaller relatively based on that where they are on the display. This is called distortion. Every camera or phone has it. And the problem is that every lens or every phone has different distortion based on the size and so on, and where it was manufactured and manufacturers. So this is an example of a photography from a same point on how can objects appear different just based on the lens distortion. We developed a process of phone calibration that you print out this chessboard, you measure it, and you collect 11 photographies of it in different places and different distance. And it's gonna this way we can narrow every photography afterwards and calculate sizes of the objects more precisely. So this is how we can model the trees based on photographies and already calculate the rough geometry of the stem and highlight the weakest spot. But this is not really, maybe a little bit, but not much increasing the geometry of our calculation. What we implemented then is the stem scan, for which, fortunately, you don't need any expensive hardware. You can also use just your phone, but you would have to have an iPhone, ideally iPhone Pro, which not sure if it's visible, but they have this dot, which is a LiDAR sensor that enables you to scan. LiDAR is a sensor that shoots a beam of a laser and it reflects from a nearest object and can create a point cloud of the nearest object with real size. So with the 5 photographies, you would also collect the stem scan, and this is how the results can look like. So pretty detailed. And the best thing about it, these are very nicely measured. The error rate from the iPhones can be around 2%. So I would argue that these can be more precise than, for example, tape measurement. This is the process of the data collection. So you just come to the tree, start scanning it, and trying to get rid of these colorful points on your screen. So as you can see, it's pretty swift. And under a minute, you can get a stem representation like this. And the process is that we then calculate which of the cross-section is the weakest. How we do that is that we apply the wind load, the force we calculate from the crown, on each cross-section from every 10 degrees. So, and we are always calculating with the worst value that comes out of the calculation. So for each profile every 10 centimeters, we calculate the worst value every 10 degrees of a wind load. But that's not all. As I said, we can implement device tests such resistography, pulling test, or tomography. How does it work? As I have here an example of Picus tomograph, and this is a tomogram of a cross-section. As you might know, cross-section like this from the tomogram can tell you if there is some cavity within the stem, but it's not very precise on the outside edges of the tree. But as we learned today, the outside is the most important part for the tree stability, and the differences can be quite huge. So what we are doing with this approach is that we recalculate the tomogram based on the real geometry. Here is an example from Netherlands. On the left, you have tomogram. On the right, you have cut through the 3D scan in the same height. And in this case, the tomogram calculated 18% less healthy wood than was the reality. And the wood was on the outside. So the overall increase of stability after recalculation was more than 40%. We did probably by now more than tens of thousands of tomography comparison with 3D scans. And if we learned one thing, it's that with simpler geometries, they are matching quite nicely. But as you get to more complex stem geometries, these are moving further and further apart. And for trees like these, you wouldn't even guess that the tomogram was done for this specific tree. So more complex stem geometry, the more sense it makes to recalculate it with 3D scanning. But how does it work in practice? We went through the data collection, which was 5 photographies, 3D scans, and optionally a device test. This could take you around 5 minutes just for the Adbian part. But what are the results? Let me summarize first what Adbian can and cannot do, and then I will show you reports. So Adbian only assesses a breakage resistance on the real geometry. So it cannot calculate uprooting without pulling tests. It also helps you provide visual information to better communicate with your clients, and it gives you baseline stability data for your arguments. It's definitely not replacing the expert. It's not for every tree. It's maybe for 5% of the biggest and most important trees. So it's not an inventory app. And it cannot calculate inside without tomography. And it cannot give you overall stability, only biomechanical stability with some limitation and some presumptions, which are important to understand before using this tool. So let me share report with you. Okay. Here is a example of report, which can be printed easily to PDF, translated to different languages, and transposed to other units. So the main number in the report is a safety factor, which if it's above 150%, generally in tree biomechanics, means that the tree should be stable. As you can see, this tree has a basic safety factor of 652% in the weakest spot, which is quite good. But then we attached tomography and it's changed the overall calculation. So here is 3D representation of the tree, which you can visit and play with more under this link. There are the 5 photographies, in this case, actually 6 photographies, because there were 3 photos of the whole tree taken and 3 photos of the stem that are referenced over here with the distance. As you can see, pretty big tree with huge cavities and fruit bodies. So definitely a hard case for an arborist consultant. So we selected the crown and did the wind loading analysis on it. As you can see, these photos could be taken from a little bit more further, but sometimes it can be limited by your surrounding. And then we calculated the safety factor every 10 centimeters. So as you can see at the base, the safety factor was around 1,800, and it was constantly dropping up to 3.2 meters, where was the weakest spot, 652%, still pretty solid. Here you can see also visualization of each cross-section every 10 centimeters. This page is for theoretical residual wall, meaning calculating theoretical scenarios. What would happen if the weakest spot had a cavity and also a safety factor, and then an overlap with tomography. So you can see that one tomography was done in 2 meters, which dropped under 150% by combining it with tomography. And this one in 3 to 3.1 meters, it dropped even below 100%. So actually, this tree isn't in the best shape if we calculate the 3rd stage of decomposition as our reference point. So we have also here the last page, which is pruning, with which we've been able to calculate that with 6-meter pruning, and this was a big tree, it has 23 meters. So with 6-meter pruning, which could be pretty drastic, you could get the weakest point to above 100%. So this tree will probably need some pruning, but it's gonna give the tree another fighting chance, so the consultant doesn't have to cut it down. So back to my presentation, and I have here just a summary that we can also calculate the tree based on the whole tree lidars, which we are piloting with several our customers all over the world. For example, in Taiwan, which is closest to Japan from our customers. Also wanted to give quick thank you to our amazing team, where we have several PhDs here from Brno that are making sure that the arboriculture know-how is correctly implemented in our calculation. I would like to thank you for your attention. Arigato gozaimasu, and I would hope to see you on other opportunities in the future. Thank you.